Hey, welcome back. How did you go with the McDonald's sign and all that dynamo stuff on the calculator? I've got some answers here for you, and let's go through and see what you found first of all. Look at this one here. In y equals ax squared, what does that a do? It affects the steepness of the graph, doesn't it? The steepness of the graph. And if you come over to the right here, I've got some examples. 2x squared is steeper than x squared. Half x squared is less steep or wider, narrower, wider, and all those words you can use as well. How did you go with that one? What about in y equals x squared plus a? What does that a do? It affects the, what would we say? Vertical position, maybe. The vertical position. Okay, so what's that? This is over here, right over on this side now, where we've added 3 or taken 4. It's moving it up and down. This is called actually a translation vertically or in the y direction. Translation, moving the whole graph vertically. Or, and the last one, x take a, affects the horizontal position. Horizontal position. Okay, so that means left and right here. So this is this one over here. It's translation in the x direction or translation horizontally. Okay, and can you just notice here, if it's x take 1 squared, actually moves it across 1. If it's x plus 2, moves across neg 2. We'd like to investigate that a little bit later on, I think, as to why this is happening in our graphs. But at the moment, what we're saying is, can you just notice the effect on the graph of y equals x squared when you do these changes to the function? And there's one, of course, that I've left out, this one here. I gave a hint to you, should try some negative a's. And here, if you've got y equals x squared and you change it to y equals neg x squared, what happens there? It's a reflection in the x-axis, as if this was a mirror, the mirror on the x-axis there, a reflection in the x-axis. Points above become negative. Below, I think you can see that. 2, 4, if you multiply by neg 1, would become 2 negative 4. So that negative in front of x squared down there is going to make all the usual positive values of x squared all negative. So again, a reflection in the x-axis. So are you starting to see the idea here? We're getting some powerful tools, and what we're going to do now is have a look at Pearson's textbook, some of these clippings here from Pearson's, and then later on I'm going to show you the combination of all these and see how you went with your McDonald's sign. So I hope you've got yours ready there, because I've got one for you, and I wonder if you did better than I did. Let's go and have a look at summarising everything that we've got now. Okay, so coming down here, let's go to Pearson's, and the first thing that they're talking about here is for each of the following equations, state the dilation factor. Now, let's introduce some words here. When you are introducing a number in front of x squared, 4, a quarter, or the neg 3 there, this produces a stretching or steepness, doesn't it? So that transformation is called a stretch. The IB programs like that word, or a dilation. That's what we're calling it. Dilation of pupils, opening and closing of the pupil, stretching. So here it's a stretch or a dilation. So determine whether the graph is narrow or wider, and roughly graph it on a set of Cartesian axes, or y equals x squared, and show what's happened to it. So let's look at the first one. A is 4, the number in front of x squared is 4. So that's been stretched by a scale factor of 4. That's what we say. And the graph is therefore narrower. So trying to draw it, there's x squared, you draw it somewhere in there without accurately plotting a lot of points. You could accurately plot points if you wanted to. We're just getting the hang of it now. Having done it on the calculator, can you do it by hand and get a good understanding? All right, let's look at the next one, a quarter x squared. the number in front is a quarter. So the dilation or stretch factor is a quarter. And the graph is therefore wider. After you've found x squared, there it is there, you put a quarter in front. So all those values are going to be a quarter of what they were. Can you see why it is flatter or wider? Okay. And the turning point, of course, hasn't changed here. We're just doing a stretching on it. So they're all still going through 0, 0. The turning point or the vertex of the function is what we often call it here. Okay, let's look at the last one. Coefficient of x squared here is -3. The dilation factor we don't usually say is -3 here. We'd say, well, it's been reflected in the x-axis. Okay, that's one transformation. And then the stretch is by a factor of 3. Usually separate this negative and take that as reflection in the x-axis. It's okay to call a dilation factor of -3 or a stretch of -3, but usually we try to split the two operations. So here's x squared, and there, if you like, if we go down here, when we do 3x squared, it would be steeper, and then we reflect it with a negative going down there. Okay, so it's been reflected in the x-axis. They actually mention that over here eventually there. So I'd split those two transformations, those two changes, into a reflection and a stretch. Okay, you're getting the hang of it? Actually trying to do it by hand now so you can get up close and personal with it. Let's have a look at the next change. The next change was where you had x take a, so it could be take 1 or x take -2, which would be x plus 2. And this is going to translate the graph or move it along in the horizontal direction because we're changing the x term. So there's the x term, x squared. And before we square it, we're actually changing it to x take 1 or x plus 2 and then squaring it. So this affects movement, if you like, horizontally in the x direction when we change the x term. So just look carefully at that. We're changing the x term. Let's have a look at some examples there as well. So here are some examples. Y equals x plus 1.3 squared and y equals x take 2 squared. Okay, state the translation of the graph. Well, x plus 3, it's the opposite movement, isn't it? When we had a look at that before, we found when you did that, it moved it plus a in the x direction, opposite to that number. Okay, it moved it across the x-axis, opposite to that number. So if it's plus 1.3, it'll move it neg 1.3 over here to the left. It's the opposite to what you might expect there. Is there a reason for that? Later on we want to unpack that and see if we can explain why the movement in the x direction is the opposite to that sign. Okay, what about the second one now? Same thing, x take 2. This is y equals x take 2 all squared. And so it's moved it plus 2 in the x direction. You can see the new vertex now, okay, and we should be stating here the turning point or the vertex is now, where is it? It's now 2, 0. It's a straight move along the x-axis or a horizontal translation, it's called. All right, translation, moving across. Right, let's have a look at some more. We're summarising everything that we did in the last presentation with technology. So here's the one where we said it's x squared, don't change the x term, but we'll add an a on the end. What does that do? And of course it moves it up or down depending on the sign of a. So this is a vertical translation, moving it up and down here. Okay, no change in the steepness of the graph, no dilation or stretch here. Let's have a look at some examples. Can you use your knowledge now to draw the graph without technology? Y equals x squared take 3. Alright, well there is y equals x squared, and taking 3 will be translated 3 units down. Once you get the squared value, you subtract 3. Okay, once you square x, you subtract 3. Can you get an idea of why it drops down now? The vertex was at 0, 0, and the vertex now is at 0, neg 3. Okay, because every value, when you square x, every y you get, after squaring, you subtract 3. What about x squared plus 2.5? Well, same thing. You're adding 2.5. This is an easier one. It's in the same direction as the number. So x squared plus 2.5, take the vertex, add 2.5. Every point, square it, then add 2.5. So they're all going to move up. So this is a translation, a vertical translation, if you like, of 2.5 units. And so the new vertex is going to be at 0, 2.5. Okay, getting the idea of it? It's good fun. We're heading off now to doing some problems, but I've still got to answer the question, is how do you do a McDonald's sign? So let's come down here. Oh, there it is. Okay, so we'll just go up just a little bit there and just get this in there. Okay. Now, combine translations. We can combine horizontal and vertical. Okay, so what would you get? Well, what's the horizontal? That's x, take a number. Okay, so that would move it h in the x direction. And then, if after that we added a number on the end, call it k. By convention we use h and k. Can't use a everywhere because it would confuse them all. So this would move it k up the axis or down the axis depending on whether k was positive or negative. Okay, so let's have a look. 0, 0 would then go across to hk, wouldn't it? Here's our x squared function. I've moved it across here. So what is this? This is 2 in the x, and it looks like 3 in the y. So my function would be y equals x, take 2, remember, opposite sign, plus 3. That's assuming there's no stretch here. The shape of the steepness is still the same. What about this one over here? A bit of funny business has been going on here. It's been moved 2, 3 again. So this would be y equals x take 2. Can you see that vertex is 2, 3? X take 2 squared plus 3. But there's a neg, isn't there? Because upside down it's been reflected in the x-axis. And there's also a stretch or a dilation factor we don't know there. So we can't actually put that in at this stage. But it looks steeper, doesn't it? What about the last one here? Where's the vertex? The vertex is up at 2, 10. So we can say y equals, well, first of all, it's negative, isn't it? Because it's upside down, if you like. This is called concave. Right, because it's like you're sitting in a cave there. There you are in a cave. So this is called a concave parabola, these two here. Concave, we'll talk about that a bit later on. So it's going to have the negative to reflect in the x-axis to get that cave type effect. And then it'll be, where's the vertex? Moved across to, so it's x take 2 squared plus 10. But we also might question, should there be a dilation factor or a stretch factor in there, because it does look steeper, doesn't it? I have changed the scale though, but we would have to check whether there was a steepness change. So there's a bit of business happening here. Isn't it getting exciting? We're getting into quite complicated looking functions, and of course we'll need to do the McDonald's sign. We're going to have to do these combined transformations, if you like. You want to come down and see how well I went and see if you did better than I did. Okay, come down here now. Here's my effort. Okay, and I've put this right alongside so you can say whether Huddy did any good with this. It's a bit out. It's not too bad. Did you do better? Okay, so I just did it roughly, didn't do the mathematics on it. Later on, we're going to do some mathematics on x squared and actually find exact intersection points, intersection with the axes, and so on. But just at the moment, here's the functions I went for. Okay, neg 300x take 5 squared plus, oh, what's missing there is 250, that's where I put it. Okay, and I put the other one at x take 6.5. Moved it across 1.5 there to get that overlapping piece in the middle. Okay, had to play around with that a little bit. And then I cut it off. I want to show you, you could just cut the view window here so that you only had the x-axis bit. But I've tried to use this idea here. See this in here? Going from 4.2, so that would happen to be that point, to 5.7, and, oh no, 5.7's in there, and then 5.7 to whatever that value was. So I've chopped it off at the same y value here. Okay, all along here is the same y value, I think y equals 53 or something, and found those two endpoints. Well, it's not bad. You can play around with that, but why don't you get everybody in the class to just show theirs and see which one's the best one, maybe, and see how people went. It's important to have a bit of fun with this. Remember, if you can get up the hierarchy there, Huddy's hierarchy of learning, don't just do the problems. Say, what's going on here? You can actually see it, get up close and personal with the maths, you can have a lot of fun. Okay, we better go and do some work now. Okay, and just try and rewind the presentation and see if you can get your head around what's happening here. Okay, let's go and do some work. Okay, so here's another example here with the turning points here and the two changes, the x translation and the y translation, x translation, y translation. So start off with x squared, and can you find where these dudes might be hanging out now? Okay, x take 3, we'll move it 3 in the x direction, and take 4 will be neg 4 in the y. So the new vertex will be down at 3 neg 4. So this is a pretty powerful tool, isn't it? This form here, where you have it in perfect square form, because you can read off straight away the vertex will be at hk, because we've said that's the x movement and that's the y movement, and the vertex started at 0, 0, so now it'll be at hk. Okay, getting the hang of it. We're starting to get powerful with this function, don't you reckon? Anyway, so let's look at y equals x squared again, and this time we're trying to graph x plus 2 squared plus 3, so the x translation will be neg 2, remember to change that. And this is the same as plus 3. We do want to explain later on, and you might keep thinking about this. If it's plus 2, why does it move at neg 2 in the x direction? We want to get up close and personal with that aspect. And so here, where is it? Well, 0, 0, all points have been moved, neg 2, and up 3. Okay, so the vertex is now at neg 2, 3. Good fun. Let's keep going. And here's our summary. We can use a graph of y equals x squared to produce other parabolas and to design these parabolic reflectors and all that sort of thing. Dilating it by a factor of a, so we put an a in front. If a is bigger than 1, it's steeper or narrower. If a is less than 1, between 0 and 1, that's a fraction, like a quarter, a half, it's wider. Do we get that? Yeah, it was more like that. Usually it's like this. Yeah, do you get that idea? Okay, it's wider or less steep if you like. Reflecting it in the x-axis. If a is less than 0, let's just check that again. There is x squared. And if you multiply it by something like neg 1, it's going to be a reflection down here. Y equals x squared. Multiply all the values of y by neg 1. That one's going to go down to there. And so it's a reflection in the x-axis to produce a function y equals neg x squared. Okay, and then of course if we do them all together, h units horizontally and k units vertically, then we're going to get that overall function y equals x take h squared plus k. So we're getting some power into our quadratic function here by taking our parent function y equals x squared and being able to change its shape or transform it into a different looking function. Okay, let's go down and have a look at some more here. Using the graph shown, find the equation of curve. Hey, now this could be powerful. You could plot out on graph paper the shape that you wanted, and then to do your computer-aided design, you need to formularize that. You want a formula for that shape. Well, here, what can we do? We can actually find it because we want a vertex at 3, 1, so we know the form for the function. It was at 0, 0, y equals x squared, moved across 3 and up 1, so it's going to be x take 3 squared plus 1. Okay, based on the turning point. And we're going to say there is no dilation. We actually haven't checked that. No dilation. We're saying that this is exactly the same shape as x squared was. No dilation there. Okay. We're going to learn about how to handle it if it has been dilated or stretched later on. Okay, come on down and have a look here at some work that I want you to do, please. Okay, so these exercises are from Pearson's now, and I'm going to show you the first 9, and I want you to pause the presentation and then later on look at the solutions as I scroll down below there. So let's have a look at the first 4 there. Okay, so pause the presentation and have a go at drawing these graphs. Okay, let's look at 5 through 9 now. See if we can get them all on there. No, not quite. So that's 5, 6, 7 and 8. Just getting a rough idea of how to draw these graphs now. They're sketches, not tremendously accurate plots. Just looking at capturing the transformations that have been done. Let's look at number 9 now. That's a complete set there, 1 to 9. And down below I've got some answers for you. So pause that, have a go. Okay, here we go now with the solutions to that set. This is question 1 and 2, part A at least. How does your graph look? I mean, you can plot it accurately. At least get the right change in shape and form. Okay, let's go to question 2. Question 2. Check your position. Does it look like that? And then question 3. Okay, question 4 then. 4, we probably get 4, 5 and 6 on there. And 7, 8 and 9. Okay, how did you do? Are you happy with that? You could check it with the calculator, of course. You're going to have technology handy by there, so that's always good. And you can always pause the presentation, go back and see it all emerging again. All right, let's do some more problems now. So come down and let's do the understanding ones from Pearson's here. So again, I'll show you the problems, pause presentation, and I'll show you the 3 answers to 10, 11 and 12. Use these hints here so you're really getting familiar with what's going on. Okay, so pause it now for 10, 11 and 12. Let's have a look at the answers now. Just see if we can get them on there. I think we can. 10, 11 and 12. Did you get that? How did you go? Think about it. Check with your teacher, check with others, and discuss it. That's always good. Let's go and do some more now. Go to the next level, reasoning. Okay. I'll pause that there, 13, 14 and 15. Getting a bit hard, more wordy problems. So with worded problems, remember now, underline the key words is always a good idea so that you can get more meaning out of what you're reading there. Okay, let's have a look at the answers now. There we are, 13, 14 and 15. How you going? Getting some ideas here? And we'll just go to the last ones here, the extension ones, the open-ended questions. Okay, so there's question 16 and 17. The answers just popping their head up down the bottom there. And of course, you'll have different answers depending on how you want to handle the problem here. So pause that, and now let's have a look at the answers the book is offering here. Okay. And they've got some general statements there. Okay. All right, how are you going? It's been quite a journey, hasn't it? We've gone a long way in a short time, so go back over, think about it, make some notes now maybe at this stage. Have you got a notebook that you could summarise what you think are the key points, the points that have come up for discussion and what we've been able to find through technology and so on? All right, there are several more presentations of this because this is a very important function. It's the first one of polynomials. It's a gateway to polynomials, the quadratic. So I hope to see you again soon. Catch you in the next presentation.